So whole body control is about achieving locomotion and dexterous manipulation. But we must endow at the same time anthropomorphism, that's sort of poetical, right, to me, to increase our understanding of a robot's behavior. And towards this end, especially in the dexterity, we've been developing a locomotion, a computational process by which legged robots can quickly recover from continuous disturbances, such that they can walk and operate nimbly alongside us, which is what we really want, right? So the beauty of whole body control was, and it still is, that tasks and constraints are the building blocks for many possible nimble and autonomous behaviors. Those blocks constitute mathematical abstractions by which robot behaviors and human-robot interactions can be described and executed regardless of the robot morphology. Versatility, in other words. Once I became a faculty a few years ago, I hired the services of Meka, probably you remember, to build this robot Hume, a robot made with 6 viscoelastic actuators, not ideal for locomotion. But we did it in a smart way, in a way. Nick Payne and I, Nick is somewhere hiding over there, right? But especially Nick, spend time over Meka. So when you hire a company to do something, make sure you send your engineers. So, you know, we learn the good ways, we'll also learn the bad ways. And obviously learning the fantastic technology of robotic viscoelastic actuators. So as part of Nick's thesis, he went on to reverse the drive of prismatic SIA, what we call now reaction force SIA, using the carriage as ground and having the motor drive to drive the ball nut. The result was a significant reduction on volume, weight, and of course a net gain on power density. And on we went to NASA Johnson Space Center, where the RFCs appear in several of the joints of Valkyrie. We also learned tons at NASA from, I guess, frustration and excitement at the same time, but especially the trade-offs between torque feedback control and impedance control aggravated by communication delays. And that has been something we have carried on in all our process to date, and I don't think we'll be in the same place where we are today without this frustration and understanding of the frustrations. So we also started developing simple methods for Valkyrie locomotion. As you can see, for those of you who begin research, like locomotion requires expertise in so many domains at the same time, you know, theory and execution and hardware and so on and so forth. And we did it focusing on the concept of keyframe apex states in a way, equilibrium point for passive ankle biped behaviors. Passive ankle bipeds are so much more exciting. They have to keep falling all the time. They're incredibly responsive to disturbances. They can ideally rub shoulders with you and walk alongside you, which is one of the targets of this research. We went on to devise tools for locomotion planning in the vertical direction, which we thought was more rare, since everybody was working on horizontal locomotion. Let's go vertical. That was a strong motivation. You see here, Nick, actually, he was risking his life. He had health insurance, actually. You know, the US is rare sometimes. And then we'll not enter here, but we use this notion of keyframe states. We use inverted pendulum dynamics to an extent. We use multi-contact, and we find switching states in a very, very neat way. That was really our methods, where they came from. And that was neat also because it allows us to reason in the phase space using keyframes, grounding them into symbols, much in the same way that we saw before, and then use symbolic reasoning to navigate complex environments. And this research, one of the students, Yes Shao, now became faculty at Georgia Tech, so we want to expect a lot from him. Here are some results from Ye, actually, where a robot model achieves agile behaviors depending on the conditions in the terrain. And we base these in game theoretical concepts for symbolic reasoning, where the environment is treated as an adversary. So exciting, really exciting research. Let's call it intelligent locomotion. Probably has been used just for today. Around the same times, we started experimental, we're talking about 2014, just imagine it in your head, to the phase-space planners and how control perfume. That was early research, and as you can see, we call that drunken behaviors because it was not quite there. For us, another 3 or 4 years. Especially that it triggered for us to, we're facing significant challenges. For instance, buckling of the structure, mechanical structure, the legged structures, that left much uncertainty on the foot landing locations. And also the aging electronics, as probably many of us face from Meka at the time. Fortunately, Apptronik came to the rescue and designed new embedded electronics. We designed part of the legs mechanical for stiffness. To a certain extent, we consider locomotion as a stiff process that can be discussed here with the community at another time. And also, we incorporated a higher quality IMU, a tactical IMU. It's not quite the KVH, but it's the STEAM 300. Actually, normally price is 6K. We got it for 1K for academics, so do use those advantages. To handle contact disturbances, we conducted the following stability analysis to determine the maximum uncertainty tolerable. So linear vector pendulum dynamics are known to be x double dot equals omega square x, where omega is a constant. They can be solved analytically to yield on the right side center of mass position and velocity behavior as a function of the starting state. We know that this process is exponential. So we need to stabilize them. So in this model, in this graph, the position PT of the foot can be treated as a stabilizing feedback process if you want to quantize per step. Is the position per step constant? It's easy to write equations of motion in matrix form where Qt is the center of mass state vector, and Q0 and P0 are the initial state and desired initial foot position. Let the feet change at continuous times t equals 0.3 seconds. So we set that as a parameter. Every 3 times per second, we switch feet positions. The center of mass after time t will be a function of the initial state and foot position previously. The center of mass at time 2t will be a function of qt and pt, and etc. So in general, we can write a discrete dynamical system where k represents quantum steps, not time. So notice here that A and B matrices remain constant for this discrete transition. Actually, if you take G gravity and h 1 meter, the height of the center of mass, it has actually specific numbers, very simple matrices that we can use for our initial testing. So we then use a concept that we call time velocity reversal. It consists of reversing the velocity of the center of mass at the chosen time, t prime smaller than t. The velocity equation is shown here. We can solve for p0, the position of the foot, down below in the middle. The desired position to reverse velocity. So this is where I have to place my foot at time 0 in order to reverse the velocity of the center of mass at time t prime. And if we substitute that into our dynamical system, exponential dynamical systems, we get the usual feedback form that hopefully is going to converge to 0 in position and velocity. We do some MATLAB code, we go there. So if you don't stabilize the system, here are the exponential dynamics, center of mass. In just a few seconds, you are pretty much in the moon. As we know, walking is harder than falling. And here is the dynamics once we add feedback, which we can see in position and velocity, converges to 0 with an initial disturbance of 0.3 meters per second, and then quickly you can see the time to velocity reversal per step quantized is pretty effective. But we said that we suffer from the mechanics. We suffer from buckling of the structure. Hume and Mercury, they bow quite a bit, and that translates in errors of all sorts. And also, obviously, estimation error that everybody else suffers. So let's incorporate those into our stability analysis. And we do that by adding an uncertainty eta on the landing of the foot, P, and another uncertainty delta on the estimation of the center of mass, of Q plus delta. And we bound both of them. And the bound actually is something that is by design. We have to design those bounds. So let's set some bounds and see where we go. That's our design process. So since we reverse velocity every step, let's consider the contraction every other step. We consider the two-step contractions, the differential Lyapunov function between the quadratic states. And I have to say that most of this work is from my student, Dokyun, sitting over here. So just being a conduit of this research. It can be shown that this contraction is lesser than a quadratic equation down here in the middle on the Euclidean norm of the state, the Euclidean norm of the Q state, which is the position and the velocity of the center of mass. So this is very simple to solve this inequality, and we get that ball of radius, whatever is on the right side of the inequality, which is a function of the uncertainty of the mechanical structure, which is the landing location and the state estimation. So now we can get, we're using that, remember, we're using that for design of our robotic system, right? The Meka robotic system was not sufficient. Our controllers perhaps were not performing, but we didn't know how good we needed to be in order to achieve a stable locomotion. So by understanding the process, we were able to go back and then optimize, end to end the whole process. So let's consider the case where the foot landing location is uncertain. Here, the red ball over here, by 4.5 centimeters. We're landing the foot 4.5 centimeters away, and the state error, the state estimation of the position of the center of mass is 3 centimeters. The red ball defines the stable region in the state space. So as we can see, it includes the kinematic bounds. So it's outside the kinematic bounds. So there's no way the robot cannot take enough long steps to recover. There's too much uncertainty for the robot to recover. On the other hand, the blue ball inside this area, it has only a foot landing error of 1.5 centimeters. You're moving the foot pretty fast, 3 steps per second. You're landing what you wanted within a couple of fingers, right? An inch here in America, a couple of centimeters even in Europe, and the rest of the world. And the state error is, sorry about that. I'm starting to like actually inches and Fahrenheit and all this. It makes everything more messy, more interesting. We're going to stable and recover from impacts, right? So the whole idea is here that we recover from impacts. So anywhere that you are on the area, with uncertainty, you're going to be able to recover from rubbing shoulders with a human, which again is the final goal of these kind of locomotion processes. And in fact, this analysis, at the end, what did it trigger? It triggered our choice of IMU, and also we have additional state estimation using motion capture system for redundancy. And also, it put a bound on the whole body control performance. We use whole body controllers. We're not going to talk today about whole body controllers, but it gives us an idea of how well they have to perform. There's very interesting things at the whole body control level. We have 3 layers of feedback. Again, Dokyun is doing a great job there. And for quite a while, we had our doubts that agility and stability would be enabled by whole body controllers. But now that we knew the bounds, everything that needed to be is optimized and change all the architectures and layers in order to achieve those bounds. And obviously also optimizing the mechanics such that we have a certainty, we know how much uncertainty on the measurement of the variables and we need to have. So very, very nice process.
It's HDMI.
Yeah, HDMI is not working. Happened with all the talks.
HDMI already override like the video, audio.
Yeah, I know it's not doing it. How are you? Okay, so one of the things that impresses me of Dokyun, he spent 7 years with this robot. So when he touches it, it's like family. Where switching to me in a couple of seconds, I am more like it's a work relationship, right? But you can see the robustness of the system and the level of interaction, again, gearing towards entering a movie theater, rubbing shoulders with the holding hands, something like that. That's the ultimate goal, right? So we don't want to sport, right? In cynical. So this is in Austin, Texas. This building actually is coming down in 2 weeks. We're going to a new one with a bigger space. You can see quite a bit of recovery capabilities. It does fall. Not here, in the next video. How many more minutes?
15.
15? Gee, what was the last slide? Oh, sorry. Let me go back to the previous slide then. And then endurance testing of walking over time. These results are very recent. It's just 1 month. Now, those of you who have been successful, fine. Those of you who are on the process of being successful in locomotion, don't think that it's an easy process. As I said, it's 6.5 years. Last Christmas, we were just drinking beer and crying. Actually, I told Don Hyun, I told him, go to Korea, spend time with your family. Let's see how the future will look like. And he came back and he was like, okay, I know what to do. So don't oversimplify it. That's the rear. Rear is ugly, so I tend not to show it, but people like it. Man, sound is important. We hit it too hard. So I don't know if Nick, you want to say something? Where's Nick? You want to say something? Okay, so I'm extremely fortunate to have Nick Payne. He was one of my students, but he has been a rock star. And then we co-founded this company in 2016. He took the position of the CTO. I'm the chief brainwashing officer, actually. CTO, very nice position. It's now a company about 5,000 square feet, right? And about 16 employees, right? We do contract work. We sell actuators. We sell electronics as well. And it's super exciting. We call the honeymoon phase, right? Where everybody is like, oh yeah, everything is happy. Let's go for happy hour, and it's truly a great culture. And thanks to me, thanks to the CEO that we have a director of innovation as well. And Nick, you want to say something? No. So Nick designed this robot entirely on his own, right? Paid by me, I have to say. But it uses liquid cool viscoelastic actuators. So liquid cool increases the power density, just like Nava Sensei, right? Right. So it has a little bit of shaft. It has a little bit of bottom dynamics. It has a little bit of chassis on it. Now I say that for grounding people. It's not a problem, of course, obviously, right? And then we use elastomers. Yes. Go with them.
Anytime you want.
Okay. So it uses elastomers instead of steel springs. And the reason is because of the frequency response. So if you lose identification, you can stabilize the impedance bandwidth is much superior with elastomers. So we're hoping that this is going to be moving at extreme speeds, relatively extreme speeds. It's a biped for agility. We don't know how far we're going to take it, but hopefully we're going to be running and hopefully achieving wonderful. And again, rubbing shoulders with people on the theater, right? Ultimate goal. Couple more pictures here. It has, the ROM is fantastic. It's about like 70 pounds weight. 70 pounds weight. Am I missing anything? We just bought a KBH IMU. We're excited about it. It took us 2 years to save the money to buy it. Vision is, and we're funded already for the upper body as well, which is going to be a completely different upper body than you have ever seen. So next year, please do invite me again. And I think this is it. Thank you.